Welcome. This video is going to continue looking at the reactivity of acids. So in the previous video, we talked just a little bit about metals and acids reacting to produce a salt and hydrogen gas. And so this next reaction we're going to look at is when you have a base and an acid combined. Now remember, a base is going to have a metal with a hydroxide group typically, and an acid is going to have your hydrogen ion with a nonmetal group. So it makes sense that you'd have a double replacement reaction, which would end up with the metal and nonmetal together forming a salt, and then the hydrogen ion and the hydroxide ion together forming water. So I put it in order. Base plus acid gives you water and salt, and gives you the mnemonic BAWS, or BOSS, or however you want to say it, but BAWS was the best mnemonic I could come up with for this. These are typically called a neutralization reaction, but it's really just a double replacement reaction, again, because you have the hydrogen and the hydroxide at the front and the back end of your acid and base. You have a metal and a nonmetal forming the anion and cation, and so they just switch places. Now, the nice thing about this is that the salt will always be soluble in water, because in a double replacement reaction, you always have one aqueous substance, and then you have a gas, water, or a precipitate. So in this case, we know it's going to be water and then a soluble or aqueous salt for our other one. So the net ionic equation is always going to be H plus OH minus yields H2O or HOH. And I like to think HOH anytime I see H2O, especially when I'm doing acid-base chemistry. So let's talk about neutralization just for a minute more here. Neutralization is used for soil, like if you've heard of people putting lime on their soil if it's maybe too acidic, or sometimes people are trying to make it more acidic if they're trying to grow certain plants. But it's often used in soil science, especially with growing plants, food, etc. It's definitely used in water. If water is too acidic or basic, that's a bad thing for the aquatic life, and especially if it's drinking water. And even your stomach, if there's too much acid present, people take an antacid to help settle it down. Neutralization reactions are always exothermic. So that we have this enthalpy of neutralization can be found in many charts. It's well known for most neutralization reactions. And it's the heat released to form 1 mole of water through neutralization. Now remember, the net ionic equation is always the same, that you've got H plus OH giving you H2O. So the enthalpy of neutralization for any reaction is going to be virtually the same. It's right around minus 57 kilojoules per mole for any neutralization reaction. Titrations then is a process done that often is done for neutralization reactions. And so a titration is a specific method that you use where you add a known concentration, a drop at a time or a certain volume at a time, until you just exactly neutralize or reach the equivalence point for your unknown. So this process is known as titration, or it's also called standardization of an acid or a base. And we'll look a little more closely at this a bit later. So looking at a couple examples here of base plus acids yielding water and salt, or neutralizations. If I have HCl plus NaOH, this is a pretty simple one because it's going to be 1-to-1 stoichiometry. I'm going to get NaCl as my aqueous salt, and then H2O as my liquid. And so my complete ionic equation would be H plus, let me get a marker here, would be H plus, Cl minus, Na plus, and OH minus. And then on the other side, I have Na plus and Cl minus, and then the H2O is not an ionic compound, so that's going to remain together as H2O. So I see I do have spectator ions of sodium and chlorine, and so my net ionic equation is just what we predicted, H plus OH minus yields H2O. My second example here, I deliberately used ethanoic acid here. This is the CH3COOH because this is an organic acid. It's also a weak acid, which we'll be talking about in section 8.4. But what makes organic acids unusual is that the CH3 group here, these 3 hydrogen are not easily released. Okay, those are bonded to the carbon and held on quite tightly. It's this hydrogen down here, the OH group, that gives up its hydrogen. So when we look at this as an aqueous solution, I'm going to have two CH3 COO minus groups, and I'm going to have two H pluses hanging out, and then I'm going to have Cu2 plus 2 OH minus, and that's going to give, I should actually have a double arrow up here because it's a weak acid. We're going to find out that it's highly reversible. And on my other side, I've got Cu2 plus, I've got the two CH3 COO minus groups, and I've got 2H2O. And when I take a look at this, again, my spectator ions are the copper and then this ethanol group or ethyl group. And so my net equation is 2H plus 2OH minus yields 2H2O, or I could reduce that to just one of each. The last reaction to look at is when you have carbonate plus acid. And carbonate plus an acid just means you have a metal with a carbonate group. And so this is just slightly different than when a metal reacts with acid, because with a metal carbonate, you have a double replacement and then decomposition going on. So what initially happens is your HCl and your CaCO3 trade places, so the H and the Ca trade places. So I end up with the CaCl2 together, and then the H2CO3 that you would expect to form in a double replacement reaction immediately decomposes into H2O and CO2. So I came up with the acronym CAWCS, and I don't care how you remember that one, but just remember that a carbonate with acid is going to yield water and carbon dioxide from the breakdown of what would normally be carbonic acid, and then your salt will be your other product. But you're always going to have carbonic acid decomposing into water and carbon dioxide. So if I look at the complete ionic equation, I've got 2H plus, 2Cl minus, Ca2 plus, CO3 2 minus, and then I've got calcium 2 plus, 2Cl minus, and then the H2O and CO2 remain intact because they're not ionic. So the copper, or the calcium, I can't read my own writing here, the calcium and the chlorine are still spectators, and this net ionic equation then is going to be 2H plus, CO3 2 minus, yields H2O and CO2. And just like we have the same net ionic equation for each neutralization, a carbonate and acid should yield this same net ionic equation each time as well. Figure out though. So write the complete and net ionic for each of these. I would suggest you pause and see if you can do these on your own, and I will pause and write my own solution as well. So as you take a look at my solutions, you'll notice that I came up with the same net ionic equation for both of these carbonates reacting with acids. Second one's a little bit messier because you have KH, you've got a hydrogen carbonate, but both the potassium and the hydrogen ion break off from that carbonate. So that's where I come up with the 2H plus. One from my ethanoic acid and one from my potassium hydrogen carbonate. So let's talk a minute about indicators, and then we'll talk again about a titration. Indicators act as chemical detectors, and they indicate a change in the environment, and they indicate a change usually by changing color. So they let us know what's going on when typically in acid base, when the pH is changing, the color will change. And different indicators will show different pH changes. So you can have an indicator showing a pH change from 3 to 4, even though that's still within an acid, or you can have it changing more near the neutral line between 6 and 7 or 7 and 8. There's a full range of indicators. Acid-base indicators can change reversibly according to the concentration of H+. So if you put more base in, it'll change one color. If you add more acid, it'll reverse back to the other color. It's usually added to an aqueous solution, or it might be absorbed onto test paper that you then dip into the solution. One of the best known indicators is litmus, and it's a dye that comes from lichens, turns pink with acids, blue with bases. But litmus paper doesn't indicate the strength, just if it lies to the acidic side or the basic side on the pH scale. Universal indicators probably used far more often because it's formed from a mixture of several different indicators, so it gives a full spectrum of color. It changes color over the whole pH spectrum and will give you an idea of strength. The problem with any indicator is it relies on your to look at the color and interpret it against the scale that's provided. But indicators are often very helpful in what we call acid-base titrations, or the standardization reactions. So a titration uses a neutralization reaction to determine the concentration of an acid or base. So in my picture here, I have a fixed volume of an alkali. So the base is what we're trying to find the concentration of. This is my unknown in the pipette. It's a known volume, and I'm going to dump it into this flask. Now you may or may not have some water in there that you dilute it with. Really doesn't matter. It's not going to change the number of OH ions in there that need to be reacted with or neutralized. You know, as I say, it's on a white tile. That's to help provide the color, for you to see the color a little more clearly against a white background instead of the black color of your ring stand, or if you had an automatic stirrer there. This column here is called a burette. It's a fancy, kind of like a fancy graduated cylinder, but it's got very small measurements on here. Ours, I believe, go to the nearest 1/100th of a milliliter. But you'd put your acid in here, and you have an acid of a known strength. Okay, so I'm going to measure an exact volume of my known concentration, in this case of my base. I'm going to add an indicator. So I put the base in here. I'm going to add an indicator to let me know when I change from a base to the acid. So something that changes at right around the 7 mark, right when these are exactly equal. And then I'm going to slowly add my acid with a known strength, maybe 1 mole or 2 molar. I'm going to add it until this just changes color, and then I'm going to stop. And I'm going to use our old friend M1 times V1 equals M2 times V2. And I'm going to know the molarity of the acid I used. I'm going to know the volume of the acid I used. I'm going to know the volume of the base I put in, and I'm going to calculate for my unknown. So this is sometimes rewritten as MA times VA equals MB times VB. And that's how a titration or standardization works.